Hi there. Just wanted to make a quick video to explain a couple things I talked about briefly in class, but you'll need for the assignment. So it has to do with the connection between a position versus time graph and a velocity versus time graph. So what I want to do is I want to look at the velocity and how do we determine velocity from a position versus time graph. I know this is position versus time because it's the position in meters over the time in seconds. So the key is that the slope in a position versus time graph is equal to the velocity of the object. And that's going to help us get from the position versus time into the velocity versus time graph. So what we can do here is we can just break this other graph up. We're going to break this up into three pieces because the velocity clearly changes. I know my graph isn't perfect, but we're going to work with it. So we'll have that section, we'll call this section A, section B, and section C, and then we'll see how I created this graph over here. So for A, we need to get the slope of this section right here. So we'll add in a little slope triangle so we can see what's going on. So this side is going to be my change in my position, which is equal to, let's say 6. So my change in position here is going to be 6, and my change in time is equal to 1, 2, 3 units. So my slope for part A is going to be the change in position over the change in time, which is equal to 6 over 3, 6 meters over 3 seconds, which is 2 meters per second. So I can take that and I can plot that, which I've done. So that's 2. So right at 2 meters per second, it stays that way for 1, 2, 3 seconds. So that's where this comes from. This is the velocity for this time period. Then we get into part B, and you can see B, the position doesn't change. So there is no change in position. So the slope of part B, I know you could probably look at it and say that it's 0, but let's see why. So there's no change in position. So it's 0 meters is the vertical change, but it happens over 1, 2, 3, 4 seconds. But 0 divided by any number is just 0 meters per second. So for the next 4 seconds, 1, 2, 3, 4, my velocity is 0. So we just draw a little line right on the axis. Now we go to the next part. So this part, I'm going to draw my triangle like so, just so that it doesn't run into the calculations down below. So here my delta x goes from 6 to -6. So that's a change of -12. So it goes down -12. And we know the slope is negative because the line is going down. And my change in time is going to be 1, 2, 3, 4, 5, 6 seconds. So my slope for part C is going to be the -12 meters over 6 seconds, which is -2 meters per second. So my velocity is -2 meters per second. So I go to -2 and go for 6 seconds at -2. So this creates the velocity graph for this position graph, and the key is slope. The slope of the position versus time is the velocity. So how do I go from here to here? So let's switch colors real quick. I already used blue. Let's do this green. So to move from the velocity back to get the displacement. So what I want to know is what was the total displacement from beginning to end. So in other words, if the object started at 0, I know it ended at -6. So that's the total displacement, -6. But I can tell that information from here, the velocity versus time graph. And the key is that the area equals the displacement. So what we do is, for this little section right here, we're just going to find the area underneath this line. So the area over here, or the distance over here, this is 2 meters per second. I know those are weird units to try to measure length, but we're talking, you'll see, it'll work out in the calculations. And the time is 1, 2, 3 seconds. So my area, it's a rectangle, my area for part A is going to be 2 meters per second times 3 seconds. The seconds cancel, giving me 6 meters. So my displacement during this first little piece was 6 meters. And that's true. Look, see? It ended up at 6 meters. Very good. Let's find the area for part B. Well, part B, the displacement for just that part is 0 meters because it's 0. There's no, we can't calculate it. It's 0 times 6, which is 0 meters. So the total displacement between here and here is 0. It stayed at 6. It didn't move. So that makes sense. Now we get to this part. This part, it's not really tricky. You just got to remember. It's below the axis. So we're talking negative. So this length over here is negative 2 meters per second. And it's over, I think it was 6. 1, 2, 3, 4, 5, 6 seconds. So this area, the area for C, is going to be negative 2 meters per second times 6 seconds, which is negative 12 meters per second. So any area that's underneath the axis is going to be negative. Now to get the total displacement, we just add them up. So my total displacement is going to be 6 meters plus 0 meters plus negative 12 meters. So that gives me a total displacement of negative 6 meters, which, sure enough, there it is. So area will get us from the velocity back into the position. Okay, so slope to go from PVT to VVT, area to go from VVT to PVT. That, you can answer one of the questions with that information. Okay, the other one is instantaneous versus average velocity. So let me try to draw a curve. Okay, so let's say that this is a position versus time graph. Let me get a line on here. Sorry. Okay, if I calculated the velocity from, say, here to here. So if I want to know the velocity, so say the first 10 seconds, and say at this position it reached, I don't know, 20 meters, then the average velocity would be the change in position over the change in time, the displacement over time. So my change in position here is 20 meters over 10 seconds. So my average velocity would be 2 meters per second. But that's just telling me the average over this time period. Because you see right here, that's clearly going to be steeper. So the slope is changing as I move along here. But all I want is the average, and that's okay. What you'll learn in calculus, and we'll talk about a little bit, is that I can actually get something like that. So you see how it touches, and it just touches right at that point. What that's called is the instantaneous velocity. Instantaneous velocity. So that's at any one little nanosecond. It's so, any little tiny instant of time, what was the velocity at exactly that moment? And that's hard to calculate. You have to take calculus in order to get that for a curve, or physics C. So we're not really going to talk a lot about instantaneous velocity. You just have to know that there's a difference. That when we're doing velocity on a curve, we're not actually determining the velocity, because even if I go like this, that's still an average, because right there, the curve is still kind of outside of the bounds. And what you learn in calculus is we'll just shrink this down until it finally hits instantaneous. But otherwise, it's always average. So right now we'll kind of talk about average versus instantaneous. You're not going to really have to calculate instantaneous though. You just have to know that what we're actually calculating is average velocity. But we'll just call this velocity for our sake. There's one instance where the instantaneous velocity equals the average velocity, or there's two cases, and that is for a line. If you have a line, then the average is always the instantaneous. Because if I took this down here, you can see that if I laid it on there, well, every point in between is going to be on that line, so therefore they're equal. And then the other one is that if it's at rest, but it's still a line. So that's terrible. Imagine it's a horizontal line. The average velocity between 2 points is going to be any instantaneous velocity between them. So they'll be equal in these two cases. So now you can answer two of the other questions, or one of the other questions. All right? Okay, I'm going to save this as a PDF. I'll save both these pages. So if you want to look at them, you can. Okay? Thanks.